Let us remember the key points from Module 3. In the first video of Module 3, we covered the three types of subatomic particles, which are protons, which are positively charged, neutrons, which are neutral, and electrons, which are negatively charged. We mentioned that according to the Rutherford model, neutrons and protons are found in the nucleus, and electrons circle around them. We also discussed the atomic mass and the atomic number. We introduced the nuclide symbol that consists of three parts: the element symbol, the atomic number, or number of protons, and the atomic mass. We also discussed the isotopes and mentioned that for any element, you might find different isotopes in nature. We defined isotopes as an element with the same number of protons but different number of neutrons. Isotopes have different abundances in nature. The final concept we covered in this part was the atomic mass unit. We mentioned that the standard for this unit is the isotope carbon-12. In the second part of Module 3, we discussed the energy levels of atoms. There are 4 quantum numbers to describe the electron energy state in an atom. The first number is called the principal quantum number, or the shell. The second is the subshell. The third number refers to the shape of the subshell, or what we call the orbital. And finally, the last number is called the spin. The first energy level, N1, is called the ground state with one subshell, S. The shape of this subshell is a sphere, and the spin is represented by an up or down arrow. After that, we discussed the electron configuration and orbital diagrams, and the guidelines to fill in the energy levels. Following from here, we discussed the periodic table in terms of the electron structure and explained how elements are positioned in the periodic table. Finally, we discussed how you can use the periodic table to predict the charge for some Group A elements. In the third part of Module 3, we looked at naming inorganic compounds. The first task is to determine the type of your compound. So you look at the first element. If it is a non-metal, then you have a molecular compound. To name these compounds, we use prefixes. If the first element is a metal, then you have an ionic compound. Before you name the compound, you need to decide whether the metal can take only one charge or can take more than one charge, like certain transition metals. If the metal can take only one charge, then we name it first. Then we name the non-metal by adding "-ide". If the metal can form more than one type of cation, we need to use Roman numerals in the naming system to indicate the charge of this metal. Remember that you can predict the charge of the metal by using the non-metal element. Finally, here are the 6 polyatomic ions and the 3 acids that you need to learn for this course. Now, let's move on to Module 4. Today's topic is related to chemical bonds and molecular geometry. Module 4 will be covered in 2 videos. In the first video, we will investigate the different types of bonds. Then, we will learn how to draw Lewis structures for atoms and molecules. After that, we will learn the concept of electronegativity and how it can affect the bonding nature of compounds. In the second video, we will learn how to draw Lewis structures for compounds. Then we will investigate the exceptions for the octet rule. Finally, we will cover the molecular geometry by studying the VESPER module. The learning outcomes for the first part of Module 4 are: differentiate between ionic and covalent bonds, draw Lewis structures for atoms and molecules, explain the concept of electronegativity. Chemical bonds refer to the forces that exist between atoms to form compounds. There are 3 types of bonds: ionic, covalent, and metallic. Our focus in this course will be on the first 2 types, the ionic and covalent bonds. In a nutshell, ionic bonds happen in ionic compounds between a cation and anion, so there is a total transfer of electrons from the cation to the anion. Let's use sodium chloride as an example. The sodium is a cation, and chloride is the anion, and these two ions are attracted by ionic bonds. Covalent bonds happen in molecular compounds when atoms share electrons between each other. The electrons that get involved in forming those two bonds are the valence electrons. We learned previously that metals tend to lose electrons and form cations. For example, metals from group 1A lose one electron and form a positive 1 ion. Metals from group 2A lose 2 electrons to form a positive 2 ion. Non-metal elements tend to gain electrons and form anions. For example, elements from group 6A gain 2 electrons, and group 7A elements gain 1 electron. The noble gases don't form ions, as they don't receive or lose electrons. This is because they have a very stable electron configuration with 8 valence electrons. Elements lose or gain electrons to obtain stable structure similar to the noble gases. In this stable structure, the elements have 8 electrons in the outermost shell. We use the term octet rule when there are 8 electrons in the outer shell of the element. For example, sodium has 11 electrons. The electron configuration is 1s2, 2s2, 2p6, 3s1. 3s is the outer shell with 1 electron, so sodium has 1 valence electron. When sodium loses its valence electron from 3s, the electron configuration becomes 1s2, 2s2, 2p6. 1s2 is the inner shell, and the outer shell now is 2s2 and 2p6, and there are 8 electrons in this shell. So sodium ion has achieved the octet rule and now has a very stable electron configuration similar to the noble gas. Remember that sodium has 11 protons, which have a total of 11 positive charges. Because it now only has 10 electrons, it becomes a cation with a positive 1 charge. Similarly, chlorine has 7 valence electrons in the outer shell, so it needs to gain 1 electron to have 8 electrons in the outer shell, and consequently a very stable electron configuration. Because the chloride gained 1 extra electron, it forms an anion with 1 negative charge. We use Lewis structures to represent the valence electrons in an element. For example, boron is element number 5, so it has the following electron configuration: 1s2, 2s2, 2p1. 1s2 is the inner shell, so we don't take this into consideration. 2s2 and 2p1 are the outer shells, which means there are 3 valence electrons for boron. To draw the Lewis structure, we write the symbol of the element and then we draw 3 dots around the symbol to present the valence electrons. You have the option to draw the electrons as a pair and single dot, or 3 single dots. To predict the number of valence electrons, you can do the electron configuration as we did in this example, or you can look at the periodic table and predict the number of valence electrons using the group number. For example, group 1A elements have 1 valence electron. Group 4A elements have 4 valence electrons. We will cover more examples of the Lewis structures in the tutorial. Now let's discuss the ionic bond in more detail. In ionic bonds, we have a total transfer of electrons from one element to another. Ionic bonds refer to the electrostatic forces that exist between elements with opposite charges. We will use the example of sodium chloride an ionic compound that consists of a sodium cation and a chloride anion. The ionic bond forms as a result of electron transfer from the sodium to the chloride. To explain this process, we will look at each element separately. Sodium is a metal from group 1A, so it has one valence electron, and it donates this electron to other elements like chlorine in our example. The neutral sodium element has 11 protons, which are positively charged, and 11 electrons, which are negatively charged. Losing one electron changes the atom to a cation with one positive charge. If you look at the neutral sodium diagram and compare it with the sodium cation, you can see that the electrons get more attracted to the positive nucleus, as there are more positive charge than negative charge. So the cation is smaller in size than the neutral element. In terms of the electron configuration, the sodium cation has achieved the octet rule, with 8 electrons in the outer shell, so it has a very stable structure. Chlorine also wants to form an octet, and it does that by receiving an electron, as it has 7 valence electrons. This electron is donated from the sodium. Chlorine has 17 protons and 17 electrons. When it gains an extra electron, it changes to an anion with a -1 charge, chloride. As there are 18 electrons and 17 protons, the size of the atom increases and the electrons become less attracted to the nucleus. In terms of the electron configuration, the chloride anion achieved the octet rule, so it has a very stable structure. Remember from Module 2 that ionic compounds form crystals. So if we look at the solid sodium chloride, table salt, at the atomic level, we find that each one of the sodium cations is actually attracted to 6 chloride anions by equal forces. Likewise, each one of the chloride anions is attracted to 6 sodium cations by equal forces. So the formula NaCl uses the lowest ratio of cations to anions, as in this compound we have the same number of cations as there are of anions. So in ionic compounds, we don't have molecules, but we have crystals. The forces of attraction in ionic compounds are very strong, and we require lots of energy to break this bond. This results in the high melting point for sodium chloride at around 800 degrees Celsius and a boiling point around 1400 degrees Celsius. As opposed to the crystals formed by ionic compounds, molecular compounds form individual molecules. For example, in 1 milliliter of water, we are able to count how many water molecules are present. Covalent bonds form when one pair of electrons or more are shared between atoms. For example, the hydrogen molecule H2. We have 2 atoms of hydrogen bonded together. In hydrogen, there is only 1 electron, so it has 1 valence electron. This structure is not stable, and hydrogen wants to get to the helium structure that has 2 electrons. Those 2 elements are exceptions from the octet rule that we mentioned previously. In the hydrogen molecule, each hydrogen atom shares its electrons with the other, so each hydrogen atom then gets 2 electrons around it, which gives it a similar structure as helium. The sharing of 2 electrons forms a single covalent bond linking the 2 hydrogen atoms together. The covalent bond happens due to an overlapping of the orbitals. So in the example of hydrogen, the 1s orbitals from each atom overlap when the atoms come closer, resulting in the sharing of electrons and the covalent bond. Another example is chlorine, which has 7 valence electrons. Drawing a Lewis structure for chlorine shows 3 pairs of electrons and 1 single electron. When 2 chlorine atoms come closer, they share their single electron and form a single covalent bond to have the octet rule around each atom. Again, the sharing happens due to the overlap in the p orbitals between the 2 atoms. We said that the chlorine atom has 7 valence electrons. So when the two atoms come together, they have a total of 14 valence electrons. However, because the two atoms are sharing electrons, they have both achieved the octet rule. We can use Lewis diagrams to show the structure of molecules. To do that, we put the two atoms and place dots around them to represent the valence electrons. For example, the H2 molecule. Other examples are fluorine, bromine, and iodine, which are halogens that belong to group 7A, so they have 7 valence electrons. Therefore, they will form similar covalent bonds as the chlorine. In some cases, elements need to share more than one pair of electrons to achieve the octet rule. For example, oxygen has 6 valence electrons, so it needs 2 electrons to achieve the octet rule. When two oxygen atoms come together, they have 12 valence electrons. So for the oxygens to achieve the octet rule, they need to share 4 electrons altogether. So the first oxygen atoms share the 2 electrons, and the second atom also shares 2 electrons. This results in a double covalent bond. Nitrogen molecule has a triple covalent bond between the 2 nitrogen atoms. We can replace the shared electrons by a dash to represent the bond. 1 dash means a single bond, 2 dashes for a double bond, and 3 dashes represent the triple bond. In the previous examples, we had 2 similar atoms forming a molecule. This means that the 2 atoms share the electrons equally, so on average the pair of electrons spends equal time around each atom. However, most of the molecular compounds form from 2 different atoms. Thus, the molecule will not be symmetrical and the electrons are shared unequally. Although the 2 atoms share the electrons, because the atoms are different, they will have an unequal sharing of the electrons in the single covalent bond. This causes the electrons to spend more time around one atom than the other. The atom that attracts the electron more obtains a partial negative charge, while the other gets a partial positive charge. We call this type of covalent bond a polar covalent bond. This attractive force that an atom has for shared electrons is known as its electronegativity. Let's look at the example of HCl to explain this concept. In this molecule we have 2 different atoms, the hydrogen and the chlorine. The 2 atoms share the electrons, but because the atoms are different, they have an unequal sharing of the electrons in the single covalent bond. The chloride pulls the pair of electrons more towards it, so the electrons spend more time, leading to a partial negative charge of the chloride. Because the hydrogen is missing the electrons more often, it obtains a partial positive charge. To represent this charge, we use the symbol delta plus and delta minus. We can also represent that by drawing an arrow towards the partially negative atom. How is this different from the ionic bonding then? In the ionic compound, one atom takes a full positive charge, which means it completely lost the electron. The other atom takes a full negative charge, which means it completely gained the electron. So there is a total transfer of the electron from one atom to the other, and there is no sharing of electrons. In a covalent bond, we still have sharing of the electrons between the 2 atoms, but the electrons are spending more time around one atom than the other. We call this type of covalent bond a polar covalent bond, to indicate that one atom has a partial positive charge and the other has a partial negative charge. The following table displays the electronegativity of the elements in the periodic table. You can see that the table has a similar structure as the periodic table and element positions are similar too. However, you notice that the noble gas group is not included because they have very stable electron configurations, so they don't need to lose or gain electrons. The table has three-dimensional representation to indicate the electronegativity values. So the higher the element means it has a higher electronegativity value. You can see that fluorine is the highest element with a value of 4. So fluorine is the most electronegative element in the periodic table. This means that fluorine will attract electrons more than any other atom. You don't need to memorize these values, but you could learn the relative electronegativity. For instance, if you remember that the fluorine is the most electronegative element in the periodic table, then as you move down, the electronegativity decreases. Also, as you move right to left, the electronegativity also decreases. For example, oxygen is higher up from phosphorus, so it would have a higher electronegative number. In terms of electronegativity, the most elements that we are going to use in this course are hydrogen, carbon, nitrogen, oxygen, and fluorine. Now, how can we determine whether the bond between the two elements will be polar or nonpolar? We look at the electronegativity difference between the two elements. The larger the difference, the greater the chance for the bond to be polar. A nonpolar covalent bond happens when there is equal sharing of the electrons between the two elements, for example in the H2 molecule. A polar bond happens when one atom has higher electronegative value than the other, so it can attract the electrons more. For example, chlorine has an electronegativity value of 3, whereas hydrogen has an electronegative value of 2.1. So the difference is 0.9, which is large enough to cause polar bonding. We call a molecule a dipole if it is electrically asymmetrical, so it has a partially positive charge on one end and a partially negative charge on the other. Let's look at the water example. From the table we find that oxygen has an electronegative value of 3.5. Hydrogen is 2.1. So oxygen has higher electronegativity, and the difference between the two elements is 1.4. Thus, oxygen attracts the electrons more, and it gets a delta minus charge. The hydrogen gets a delta positive charge. We can also draw the arrows to present the polarity. So the water is a polar molecule. We call the water molecule a dipole, as it is electrically asymmetrical. As a rule of thumb, if the electronegativity difference between the two elements is greater than 1.7 to 1.9, then the bond will be more ionic than covalent. So to make things easier, let's make a spectrum that represents the difference in electronegativity. When the difference is close to 0, the bond will be nonpolar covalent. When the difference is between 1.5 and 1.7, the bond will be polar covalent. When the difference is more than 1.9, the bond is ionic. Here's some examples. Let's try to predict which of the following compounds are going to be ionic and which would be covalent. The first compound is SrCl2. We can solve this question in two ways. Firstly, from the periodic table, Sr is element number 38, and it is a metal. Chlorine is a non-metal, so it should be an ionic compound. Secondly, let's confirm this using the electronegative table. Sr has an electronegative value of 1.0. Chlorine is 3.0. So the difference is 2.0, and according to our rule of thumb, the bond should be ionic. So using either of these rules should give the same answer. Now let's look at PCl3. Phosphorus is a non-metal element. Chlorine is non-metal too. So the compound should be molecular with a covalent bond. Using the electronegative table, phosphorus has an electronegative value of 2.1. Chlorine is 3.0, so the difference is 0.9, and according to our rule of thumb, the bond should be covalent. Therefore, we can put delta positive on the P and delta negative on the Cl. Try the other examples by yourself. This is the end of part 1 of Module 4. Please proceed to the second part that will cover the Lewis structures of molecules and molecular geometry.